Is technology going to? Oh, I think
it says it's live.
It says it's live. Do you believe it?
No.
You're not Ben. Hey, hello everybody. I'm Bill Hurd. I have with me Mike Fikes. Ben's missing in action.
Hey,
he might join us here shortly. But how you doing, Mike?
Very good.
Yeah,
thanks for having me on. Yeah.
So Mike and I, we're in the Discord channel. By the way, you know our Discord channel, right?
I do.
Coriolis.
Yeah.
See, that's the lead in. That's where you go, oh, you mean the Coriolis effect?
Oh, I didn't catch it. Yeah. I'm a little slow right now.
Let me tell you about Coriolis-effect.com.
Yeah.
So go there. There's a Discord invite. Join us on our Discord. Hey, here comes Ben. Let's add him to the screen. Hey, Ben, Mike on. We're talking. How you doing?
Like every Friday's the day my computer doesn't want to boot quickly.
You should never turn it off.
Yes, never turn it off.
That's right. You're right, I know. That's what I get for building a dual quad-core 16-thread
16
Xeon with 128 gig of RAM.
Yeah.
With hamster wheel.
It's an amazing computer on paper, but when it comes to actually getting a stream going, it's surprisingly difficult.
I recently got a second DSA, one of those dynamic signal analyzers, and I noticed that one was booting faster than the other. And I was like,
oh, wow.
Is something wrong with one of them? And I looked, and it turned out that one of them had double the RAM as the other, and it was during its memory check.
That used to happen.
That'll do it.
Yeah, you used to be able to tell how much memory you had because it took a long time to write to 64K with a 1 megahertz processor. It's more than a heartbeat. So, so how you doing today, Ben? I realize it's morning for you out there on the East Coast, but we've got like some things to talk about today.
Yes, today's a good day. I actually went for a mountain bike ride, and there's this small mountain. It's really not much more than a steep hill near where I live in Southern California. Here I'm in Escondido, and there's this lake called Lake Hodges, which they've been draining lately to do repair work on the dam wall. And there's a lot of nice mountain bike trails all around the lake.
Right.
So I normally go around there, but there's this one mountain right next to the lake. It's a small mountain, as I said, called Bernardo Mountain. And twice in the spring, I tried to get up it on my mountain bike and gave up halfway up out of steam.
Did you try an Uber?
It's yeah. Ubers can't fit up there. Yeah, but today I made it to the top. So I was very proud of myself.
So you're literally coming off the peak here.
Yeah, literally.
Very cool. Very cool. So first off, I want to apologize to everybody that watched last week. I had a customer emergency. It does happen. I'm a working engineer. So I do apologize for that. Hopefully this week goes better. But before we get further, I wanted to show, let's see if I can bring it up. Boink.
Oh, it looks like a nice little
PCBWay's fifth design contest. So I'm a judge for that this year. And this year's themes are on next generation hardware, earth-friendly projects, or you can choose your own theme, and they're giving away a few $1,000s worth of cash. And
hey, I'm not a judge this year.
No, but I am.
Anson asked me to, and I declined politely. I have been for about the last 4 or 5 years.
Right.
But this year I'm trying to dive and catch so many balls. I thought, I can't, as much as I like it.
Yeah, you got to say no.
But that means maybe I could actually put an entry in it though for a job.
Right.
No,
so I'll just disavow that I know you. Call it the Coriolis entry. So hey, we've already plugged the website, so that's out of our way here today.
Well, speaking of that, when you went around, I got a little bit cheeky and showed some potential logo action. I'd like to get your reaction. This is for the site, for our show, for the Discord. Let me see if I can bring it up. 1 second. I want to show you this, Bill, but you have to be completely honest. So people,
then don't show it.
no, because, and I'll tell you why. It stemmed from the idea you sent me privately in a DM over Discord last week. I just have to remember where the heck I put it. It's this one, I believe. Except it always wants to play in DivX. I've kind of lost my like for DivX. Sorry, I'm going to find a better media player to play it in. 1 second, one second.
Not a problem.
Open with.
So right off the bat, I can assume it's an animated logo, right?
This one is. This one is. And I don't know if you went back and looked at the show. I cheekily showed it at the end. So let's share this screen.
Well, moving logos don't go well on paper, unfortunately.
No, but are we on paper?
Business cards.
This is a show. We're online. So why did that minimize? Here it is.
Oh, that's cool.
So it's the two opposite swirling storms coming together from south and north hemispheres.
Oh, that's cool.
I don't know what that one. That wasn't the actual one I wanted, though. What's the better one? Was this one, I think. Open with. I wanted to bring them together and end in an eye diagram to, sort of imply that we talk about signal integrity.
Right.
So they gradually come together. And then it kind of slows down and stops. I need to work on it some more, but
very cool.
If you don't like it, that's okay too.
No, it's cool. At the end of the day, a logo does consist of the icon, the 2D, the 3D, and the animation. So part of the challenge is, and I just heard this the other day again. A good logo looks good as an icon also.
That's right. It does.
So very cool. And what'd you do? What program did you do that in?
I modeled that in Fusion because I knew how, and I knew how to render it and animate it in Fusion. Ideally, it would have been done in Blender. Because
Blender gives me headaches.
Yeah, but at least it can do it.
Your kid knows Blender, right?
Yep.
A little bit.
Knows it. Yeah. So whenever I need that kind of stuff done, he does it for me.
Nice.
Yeah. He's young, so he sucked up the menuing system probably right into his brain. Yeah.
Maybe we can get his help and pay him some money to help us out with it.
Yeah.
Yeah. Hey, you pay him money, I'm sure I can get my kid going. He's learned the value of money. You know what he got into is Gundam. I got my kid addicted to Gundam, because I was addicted to Macross in the 80s, Robotech, and now he's building Gundams, but they cost like 60 to 300 each, something like that.
Wow.
Yeah. So
what's the definition of a hobby?
What's that?
Definition of a hobby: something that takes all your time and all your money.
Right. And isn't your wife? Yeah.
Or the IRS.
Right. Right. So Mike and I this week and last week have been trying to get Bode Plots out of a live switcher. And Mike, you ended up like getting a big honking transformer from Home Depot, right? Or someplace for the low frequency response?
Yeah.
Yeah.
I was using a mini circuits Balun, but it would not go very low in frequency. So I was like wondering if that was the problem, we were using this as the current injector or the signal injector. And the idea is you're supposed to put in a very weak signal that then gets amplified by the control loop.
Right.
And you'd see the gain of that control loop. And you got one of those?
Yeah. There's a small transformer, and I had the same problems you did, which is I can get down to about 4 or 5 kilohertz on my injection, and I can go up to 10 megahertz, but I can't get down to the 1 hertz. So I'm looking at a transformer, And you and I were talking about, can we do our injection transformers in parallel? So
for the low end, the
Ben,
high, yeah.
Ben, if you put a transformer with a high frequency response in parallel with a low frequency response, do you get a wideband transformer, or do you get just lots of interaction?
Have to do the Bode plot of that thing.
I know, that's what I thought
frequency
of.
response of it, yeah.
It would give you a composite of both, but it's a pretty heavy load.
Yeah. Yeah.
Like they might not be matched with
what,
each other.
What you really want to do is, that would kind of work, but it would be changing all the impedances everywhere, and they would interact with each other. You know what it reminds me of, Bill, is passive crossover design for loudspeakers.
Right. That's I thought it was very similar.
You're trying to solve. I mean, that's a slightly opposite problem. You're separating frequencies out,
right,
using passive, mainly inductive, but also capacitors and stuff. But there's a fundamental flaw with anything that requires inductive coupling. Is the lower you go, the more core, the larger the core you must have.
Right.
And the larger the core, the more inductance and capacitance, interwinding capacitance you're going to have too. In particular, you're going to have way more interwinding capacitance. So that's going to limit your high end. So you could probably come up with a clever circuit that does combine them.
Right.
Where one part takes over where the other one leaves off, kind of thing.
Right. And so one thought I had was then to run a Bode plot on your own injection, and you know before you start whether the circuit is going to do what you expect it to do. So
you could, if you're smart, you could even switch from one to the other.
Well, you'd have to know where the sweep is in the. You'd have to work from a trigger then, right?
Yeah. Or
if you're doing
use some of the input to detect it.
Right.
You could do it analog. Just have it separate out two different frequency ranges and have a high-low output of a comparator that says, when I'm high, you're using this. And this can be done. Comparators are pretty fast, so you can actually, this again, going back to older episodes, excuse me, where we were looking at some of those old Roland delay and reverb processors I have.
Right.
Before they had good audio codecs on the market as a single chip solution, they had to come up with their own scheme for sampling A to D and D to A, and they came up with a 12-bit companded. And there's two ways to do the companding. One, the cheaper units, like the little Boss pedals, used analog companders, and that was okay. And they're like, that's okay. They don't have as good dynamic range. They add a lot of distortion to the signal, but guitarists like distortion, so it's not a problem. Adds to the flavor of it, you know.
They like repeatable.
The studio unit in the rack, they did not want to use the analog compander. They wanted to come up with a much more clever scheme that gives a virtual additional bit of resolution to this. So basically doubles the dynamic range.
Right.
So they actually have 13 bits of sample storage, and the 13th bit came from switching circuits on the analog signal coming in that were just using 4066 switches. We've talked about the 4066 ad nauseum, right? Sample and hold, and analog comparators, LM311s or NJM311s, because they were the Japanese-made version of it. And they're fast enough to do it, and they actually improve the fidelity of the unit to be really good. So you could do it that way. You could get a comparator, have filters input to the comparator so that when the frequency passes a certain threshold, it flips the comparator on the input sweep, and the comparator then kicks in the other
right.
broadband device.
Right.
Yeah, it's a lot of work, but you could do it.
Right. So, and the device we've been playing with this week and last week is we showed it a couple weeks ago on the show, my Analog Discovery 2. And I've got a cute little BNC adapter board and my little BNC parts. And from there, we've been running a Bode plot. You want to talk about a little bit about what a Bode plot is?
Yeah, I mean,
real simple.
Or does Mike want to talk about it?
Yeah, Mike.
Okay, I'll take a stab at it. I would just say it's, just the frequency response of whatever it is that you're trying to measure. And it's you have typically one plot on the top, which is the gain, and another plot along the bottom, which is the phase, and they both are in terms of frequency. And I think if you go back in history, there was the guy Bode who created the thing, and back then I think that his claim to fame was they figured out how to do it without computers and calculators, and you'd find breakpoints and based on poles and zeros and stuff like that, and you could quickly figure out by hand what the frequency response of a transfer function would be.
Yeah. So when Mike, you studied computer engineering or software engineering?
At the time, it was aerospace engineering, but it's all the same.
Yeah, right. So that's exactly it. So in aerospace, sorry, there's a siren going past me right now.
No worries. Yeah.
I'm in the hood in Escondido. My office is
as
seriously,
long as they're
this
not coming
area
for you.
is, they put a massive iron fence around the actual office building to keep people out. Anyway, that's so you would have done a linear systems and control class.
Yeah. It's multivariable control theory.
That's one of the things. That's one of the things that software engineering students miss out on. I think maybe it's different here in the States, but in Australia, if you study, that's one of the key differences. Say, I did computer systems engineering, which is it's hardware, really. It's hardware and embedded systems, but you still do all that analog stuff. You do linear systems, you do computer controlled, and DSP. It's awesome, and it's mind bending. The first time you have to do all of that with your Laplace transforms, it hurts your brain, but it's valuable skill. But I remember that's what they taught us to do. We learnt to draw Bode plots by hand, just using straight lines.
Yeah.
And even if you go back and look at some of those cool app notes from TI and others, where they're talking about the control theory of a switching power supply reference design, that some of the old app notes even have diagrams in there. And I remember reading one from a big, thick book I had from them in the 90s. And the author is saying, we put the poles here and we put the zeros here, and then drew it out by hand, basically, and show, because here's the other part of, we call them Bode plots in Australia, because Bode sounds too much like B-Day. That's just, I'm just being silly. But the other part of it is your phase, right? So you have your frequency response that you mentioned, but under that we would, in line with it, we would plot the phase of the open loop. Was it open loop or the final closed loop of the system?
Closed loop.
It's closed loop. You plot the phase, and then if the phase is crossing 180 degrees, but you still have positive gain, then you're going to have instability or oscillation in the system, right?
Or where you cross zero gain, you check your phase margin at that point, and that tells you how close to instability. So I just happen to have a small switcher here I got off DigiKey, and it has two probe spots for, let's see if I can get it. Anyway, it says Bode plus and Bode negative. So it's actually points where you can inject your signal and measure the small. Meanwhile, this is doing big signal transitions, but you've injected a small signal that's riding around in the closed loop and measuring it. So That's what Mike and I have been doing the last 2 weeks, and we're like,
for the life of me, you can't get it to like do the right thing. So,
I can't get my gain to cross on a live running circuit. I can't get my gain to cross 0 on my injection. So I'm still trying to figure something out.
Is that
we might have the wrong
so
transformers?
what's the goal? You have a design, Mike, you're working on right now?
I just want to understand it. That's my take on it. I just want to understand.
And I'm working on a switcher, so I'm trying to test how well the Spice CAD programs that like Analog Devices and TI give you. I want to see what the PCB layout and anything else may have done to my stability. So I expect the plots to at least look similar to my simulations.
Right. Okay.
So that's why I'm digging in. And then I bang Mike because he can actually do math, and so he's my calculator.
But I can't even get the thing to make the correct plot. It's like you make a Bode plot and you're like, that's right. And you're like, I'm not sure. And it's like, you don't have anything to compare it against really. So you have to be really careful. You know, you don't want to just hook it up and say, oh, this is the Bode plot, right? You want to convince yourself that the curves are all in the right direction. Yeah.
So speaking of control loops, these things. Oh, let me try and make mine bigger. This is what's on my bench today. I've got 3 dynamic power loads. The blue one on top is a BK8500, which actually belongs to Mike. He shipped it to me to play with. Meanwhile, Mike and I both bought the Kunken. What's the model number on that, Mike?
KP 182, I see.
182, yeah.
182, yeah.
That's an inexpensive one.
It was like $219.
Or less, or wasn't it like 100 and something? I can't remember.
Was it 149? Something like that.
Something
Yeah,
like that,
cheap. Yeah.
It's really cheap.
And you can buy 2 or 3 of them for that price. And if you want to do an ATX power supply or something with plus minus 15 and 5, they're all isolated, so you can afford several for that cost.
That's cool. I have a question. Do these things just have to dissipate the energy for load as heat, or can they feed it back into the grid somehow?
They are not multi-quadrant, right?
Well, they blow the heat out the back.
Yeah.
There's a fan.
I thought they must have to. I thought they must have to, because to make a device that feeds onto the grid, you couldn't have a 3-prong plug on the end of it.
Oh yeah, that would be.
Because let's just say you plug it in, you power it up, you hook it up to your device under test. Your device under test starts generating electricity, feeding into the load. Then you could unplug the load, and you've got live prongs.
Right.
But I've always sort of wanted to do it that way, to capture that energy somehow, so it's not just wasted.
Right.
Yeah.
Right.
Maybe if it's
probably doesn't matter for this application. It really doesn't matter.
It boils your water for coffee for you or something useful. Yeah. So Mike, you took yours apart, your Kunken, right?
Yeah.
I watched the video, and we were concerned about safety.
Yes. So this outer shield is not connected to the ground. That's at the bottom. That's one problem. It's not connected.
Wow.
Right.
So it's like, you got to scratch out parts of the screws to get it to connect properly, if you care about that. And then the other thing is, and this is stuff that like VoltLog blogged about this stuff. He found that some of these screws, I think it might be the top 2, or any of the screws that are connected into the heat sink. The heat sink is connected to the positive line. So if you're like putting a lot of voltage into the positive line, and you reach around and try to switch this power switch, you're getting close to these screws.
Wow.
Right. So they used FETs, which the tab on the FET is connected to the drain, I think they said, and that's connected to the heat sink, which is connected to those screws. But they fixed it too. You found some things had been fixed. That from after we looked at the video, and there was something else in there. Something was close to grounding, and you said it's no longer close or something.
Yeah, it looks like they're aware of things, and like the PCB has a pretty modern rev date on it inside of it, so it's it's probably safe. But if you get one, you might want to be aware of those things. Like, I mean, imagine if something live touched this thing, and it's all like it's the powdered, whatever you call that, powdered
Powder
stuff. So it's, yeah, so it's like you really can't conduct through it easily, but
not without grinding down the coating. Yeah.
But the inside is the inside's powder coated as well. So yeah, maybe it's okay. I don't know.
So Ben, the ground wire was about 8 inches long and black, and kind of looped around lazily to the chassis ground. And I was telling Mike, boy, in my day, it had to be a 4-inch green wire that went immediately to ground, as soon as you came in the chassis.
I'm pretty sure that doesn't really comply to international standards. If it, even just that it's black. My understanding is it must be black.
Right?
It must be green or yellow, or yellow with a green stripe, or green with a yellow stripe.
Right. And it had a distance on it, and we used to. Part of our mechanical instruction was they actually did a machine around the ground lug to make sure there was a good surface for the ground terminal back when I did instrumentation. So now why would I say control theory and talk about power dummy loads? By the way, that's a that's a dynamic load, they call it. Yeah. It's not just a resistor.
Right. So you can actually program it to switch the amount of equivalent load, right? At different times or frequencies or whatever.
So it can do
check the response of a power supply to a varying load. That's the bottom line. You need a varying load to properly test a power supply design.
What I ran into was to properly test a switch mode power supply where I knew the wattage, I needed a constant wattage load. And I got to say, the Kunken does that. Is that your experience, Mike? It's a nice solid little, you punch in 2 watts and it'll give you 2 watts of power load.
Yeah, pretty consistent.
So you can do constant current, constant voltage, or constant power. And a resistor won't do constant power because the voltage goes up, the current goes up. Well, in constant power, if the voltage went up, the current would go down, so that E equals IR stays the same. So it's useful for a constant power load. My third box I got, let me see if I can show it, is that bottom one.
That looks amazing. That looks dead sexy, I've got to say. That's that Rigol load.
Yep. So there, it's in constant power mode there. But the reason I got this one was it has the ability to process a list. So it shows power setting 1, power setting 2, power setting 3. I've got 500 steps in here that I've uploaded from a CBS file, and it emulates my load, my dynamic real load for 1/10 of a second, and then repeats. And the idea is to simulate a true dynamic load on a switch power supply.
That is awesome.
And we think it could switch around 30 microseconds or so per step. So that's like smaller than the typical transient response of a power supply.
I know it's supposed to be good for 1/10 of a millisecond. I don't know how much faster than that it can go.
Yeah, so it's like that's what you can type into it or whatever, but you don't know if it actually can do it.
Right. So it seems it's got a constant resistance mode too, which is so what made me think to say why is that a closed loop system is it isn't a resistor. It's a it's either analog or a microprocessor that measures the voltage, measures the current, and changes the effective resistance of the load, which is probably FETs, as we talked about. So so my new toy, it's not a toy, obviously, it's for business, but I've had fun with it. And Mike had to talk me off the ledge. I got it. I'm like, this piece of, I hate this thing. I can't get the software to work right. And slowly we got the virtual terminal is how I had to upload those 500 steps. I will say this about the Rigel. The tech support guy was great. Gabe over at Rigel. He said it's counterintuitive, but you can't stick a USB stick in there with a CSV file on it and upload it. You have to do it through the computer interface. So I got the software and did all the uploading and everything.
Yeah, well, you'd really want the computer hooked up anyway, ideally. I mean, that's something I like about Rigel scopes. Even the cheapest ones, you can plug them in. The software can be a little janky, but
But
you can automate and control everything on the whole thing. So you can, and that makes sense. What they did was they built instruments that are low cost enough but flexible enough that companies doing big automated test things like assembly houses at the end of the assembly line, they could have like 20 of them on a rack, and they're all pre-programmed to run the boards as they come off the line through a series of tests. And even stuff like waveform masking, so you can put a mask and say, as long as the waveform's within this mask, we're okay. And just automate the whole thing.
Okay. Yeah.
So now Mike's been doing some pseudo automation with Scuppy. How do you pronounce it, Mike?
I would say Skippy, but I don't know how to say that. Yeah.
Well, I'm from Indiana. We say Scuppy.
Scuppy.
So Mike's got it's an 8500. Mike,
you're talking about the computer that I got?
The HP? Yeah.
It's an HP 85. Yeah, it's the old
85.
It's basically a glorified calculator that can run, it's made in like 1978, 77.
But from there, you can run SCPI commands to your test equipment, right? So you can automate your testing from, and you got interested in that by watching Curious Mark. He
has one, and to be honest, it's like, for me, like I have one of those ProLogic yellow USB to
I have
GPIB
one
adapters.
somewhere.
I have that, and that works fine. But I would like program something in Python, and then I'd go away for a few months and then go back to use it again, and something wouldn't work anymore, right? It's always like, I don't know how to describe that. You're like, what setting did I have to make the dang thing work? And it's always like, it's always difficult. And I would just resort to using RS-232 or something like that. So this HP 85 just works, It's like, that's probably one of its main use cases. And it's just, it's got a basic programming language built into its ROM. You flip it on and you just type some stuff into it and it goes. And so
does a query, takes the results, does math on it, does another.
You can do whatever you want because you can program it in BASIC. Python didn't exist back then, right?
Right.
But I could say, like, my experience was like I plugged it in and like, lo and behold, the thing was talking to the end device. Whatever I plugged it into, it actually worked,
Wow.
And that's my experience with the ProLogic stuff is it mostly works, but it's futzy. Maybe that's the right word.
I had the same thing. I had to sit there and dink with mine to get mine to work, my ProLogic to work. Yeah.
And I don't think it's a problem with ProLogic, really. It's like, it's just a complicated stack. You have like the Python stuff and then the drivers and Visa and all all it takes is one of those things to be a little bit out of line and you have some wrong version of something or it can't find some dependency and
Right.
Yeah. I know I ran into problems with those NI Visa drivers. I think you were about to mention that.
Okay.
Yeah, a lot of these instruments use it.
Rigel uses NI. Yeah.
Yeah, they use a DLL from National Instruments.
Okay,
that's right.
For I think it's like a virtualization of GPIB over a USB or something. But I've had a lot of trouble sometimes getting it to work.
Yeah. So you have the futzy feeling as well.
Yeah.
Yeah.
So somebody asked if you could use a PET. The PET was known for doing industrial and scientific back in the day. And I just remember watching a movie about a wind, and then there's a wind tunnel and there's a PET running the data acquisition of the wind tunnel. So yes, I bet you could. It's IEEE 488.
Yep. It's just a variation on like the Centronics parallel port is not that different. It had, but the 488 was better in that you could, I think there was a limitation on reading from a Centronics printer port. You could read 4 bits at a time. There was some, and that's why later on they came out with
SCSI 2 and
different versions. There was ECP, EPP.
Oh, those things, right.
But the original one was SCP or something like that. And it was write only, but you could kind of read as well, but you could only read 4 bits at a time. So it was a pain.
Yeah. I remember they made dongles for the printer port at one point.
Yeah, I have some ECP dongle software license keys somewhere for PCAD, but no one can generate an actual license anymore for them. That software was long since destroyed by Altium.
Right.
Speaking about Scuppy or Skippy, whatever you want to call it, Scuppy. If you go back
now
to
I've
like,
poisoned you. Yeah.
if you go back to some, I know now I'm not going to say it correctly. If you go back to some of the earlier HP gear, it would typically be the kind of thing where the front panel had, the buttons that you would press to do things. And typically, if you looked on the front panel, there'd be like little letters that were like encircled in boxes or what, some sort of affordances to let you know, like, this is what you would put in if you were doing GPIB. So GPIB, the early GPIB, at least for a lot of those machines, was like just an alternative way to push buttons and then read the display back out. And then I think Skippy just kind of like normalized it all and said, okay, we want to like make this abstract idea of a field in the machine somewhere that you could say query it or write to it. And it kind of like got itself away from being a way to just like poke at the front panel, really.
Right. And once you showed me the Skippy commands for the list function at 5, then I'm like, it exists. So that gave me the impetus to get the virtual instrument to upload the CSV file.
Yes.
So knowing that there was, if they didn't exist in the Skippy, then I wouldn't. Then I'd have said it doesn't do it, doesn't support it.
So you actually, did you plug Ethernet into the back or RS-232?
No, I'm doing USB.
USB, okay, yeah.
Mostly. So my thing is, I'm not plugging something from overseas in my network without tearing off a new DMZ off my firewall. So I've got it on USB right now.
Okay, but it does have an Ethernet port.
It does, yes.
Oh, that's impressive.
Which is the new state of, yeah.
So that was your first piece of Rigol gear at all, right, Bill?
That was. And again, you had to talk me off the ledge because I'm like, this piece of,
Did you like it in terms of like the build quality? Like the buttons, did they, like compared to this thing?
Beautifully designed.
This was surprisingly cheesy, the front panel. It's like,
and I was okay with that panel because it's $100. Right?
Yes. Yeah, you can't complain. I mean, I'm glad this thing exists in the world. You can buy it. And if you open it up and look, the PCB is high quality. It's just like, they really like reduce the cost of this stuff. It's like, man. Right. But the Rigol gear is not like that. It's much nicer. Yeah.
Proper backlit elastomers and all that stuff.
Yeah.
But so the thing, I was going to say, crap. Now I lost my train of thought. I wanted to ask. Oh yeah. So with the Ethernet port on Rigol gear, do they charge extra for software? Because I know like the big 3 or big 4, let's say. Scope manufacturers, if you want to use the scope on a network, you've got to pay a license fee for the software. Yeah, like the scope will connect. It will even tell you, this is my IP address. You can go to the IP address and there's just a placeholder page.
Rigol does do that thing where they do have things that are like in the hardware that you can enable by buying whatever it is and then putting in a code into the machine and enabling various things.
That's I was aware of that in their more advanced scopes, that there's extra features that are essentially licensed software features in the scope, and they've kind of made it easy to hack them and unlock them. But I'm just thinking, even for connecting to it remotely and looking at the screen over a web browser interface, like for tech, you've got to pay for that.
Right. So now my Tektronix scope, it came embedded in it for my MDO. The web browser was, and that made the Hackaday videos possible. Suddenly I could take screenshots all day long. So that was, but Mike and I were talking, was that Keysight we were looking at? And we started going, goodness, do you need a subscription just to keep your test equipment working? Have you ever heard of that, Ben? Yeah. Do you need subscriptions for the high-powered stuff?
Or for at least to get new firmware updates, maybe? Or what?
Well, that I would think you need a subscription for.
I don't know. I would think it's really just for updates to the existing thing. I'm pretty sure when you buy a scope and you buy the options that it has, that you can buy the perpetual. I know they are offering subscription software for the actual software they have for simulation and for closed loop, like so something like Pathwave, they have these really exceedingly powerful capabilities where you can simulate something then you can build it and measure it, and you can close the loop and compare the simulation in the same software to drive the scope and measure what the software was simulating in the past. It can drive the scope to measure it and then give you a report that compares the two and says, yep, it matches. And I guess you call that hardware in the loop. And you need that sort of thing for really cutting edge tech, so that whatever the latest DDR5, they're already working on DDR6 standards, if you believe it or not, but DDR5, or if you're doing like really high volume consumer goods like motherboards, or if you're doing aerospace, you need that kind of thing, and it's worth spending the money because time is everything in those markets. If you don't launch your product, if you launch 2 or 3 months after your competitor, you're done, you're out, game over. And so I know for those capabilities, you can buy perpetual licenses, but they're very, very costly.
It also speaks to the cost of testing.
Or you can pay subscription, and then it's like, well, we need this in January, February, March for the development effort, and then we're product launch, and then we'll need it again by November for the next year's push, or whatever's coming down the pipe. And if your business changes direction, it's not a problem. I think like a lot of companies, they're really pushing people in that direction. I know, like Altium will always have. I can't say always because I'm not in charge, but and not working there, of course. But I believe they will always have a perpetual license option, because they have so many customers who will just go somewhere else if they don't.
So I would, yeah. I have a perpetual license on purpose. Yeah. So here's let me see. I don't want to. Oh, there it is. There's my software version of the.
I was going to say that looks really nice.
That looks really cool.
But it's not a real one.
No, it's not a real one. But I can come in here and set, but you can't type characters, so don't think you can if anybody's looking at this. You have to sit here and push the buttons just as if you were in front of it. No.
That's such a fundamental.
So. Let me try it again.
Oh my gosh.
Like you can't press the 5 key on your
keyboard.
Oh
my gosh. They spent all their time making it look like a photo of the real thing.
Right.
And didn't actually stop to consider. Now, what is the reason why someone wants to do this remotely from a desktop versus?
I don't use this screen. I used this screen, and I used this screen to load my. Here, let's do it. I'll actually show it. So I come over here and I load 500 steps.
That's more like it.
And here's the 500 steps of my power outage or power output. You can see it 0.2 watts, 0.2 watts, then it'll jump up to 0.5 watts. So I did all this work on this in this virtual screen, but it's not a virtual instrument. But so this is what, working with Mike, I was able to get all 500 steps programmed in. So again, thank you, Mike, for keeping me on the path there.
Yeah, I mean, I'm curious if you're like going to chuck your first piece of Rigel gear out the window, or if you're going to keep it.
I almost did it to you. Yeah.
It's but it's like it's an interesting subject. Like when you're building your own lab in your house, you can't afford.
Oh, yeah.
Like
you and I talked about that.
$4,000 for each piece of gear would be like drive you broke. Like you could do that if you were like in a company and you had a shared lab that everyone was using. But if you're populating your own lab in your basement,
right?
How do you? So I'm glad these cheaper things exist.
Back in my day, a scope costs a year's salary for an engineer, so you couldn't go out on your own. I needed a $40,000 lab to do anything, to do any work, basically.
Yeah, it's still basically the same. If you want to do serious high speed stuff, or RF, microwave,
UWB, and all that.
One instrument will cost a year's salary easily.
Yeah. Yeah. So yeah, you know, I've got an eBay lab, but I started buying new stuff lately too. As you know, as I get into specific needs. But whereas Mike's got a huge collection of equipment, I kind of was the opposite. I'm like, how can I do this in the minimal amount of equipment? So I have like a counter, you know, the things that you need specifically, like 8-digit frequency counter.
Yeah. And then that 82 kind of takes it to an extreme. The 82 AD analog discovery too will do everything. Yeah. I was just thinking about the 82. What was the little thing it did that was nice? It'll do curve tracing. It'll do impedance. All this stuff. And the reason I tend to get a lot of this gear is mostly educational, to learn about these subjects, you know, these topics. And that 82 is really good because it works at frequency that's enough to learn all these things, right?
Yeah.
I like that I can use it as a floating input and monitor the current going to a circuit. So right off the bat, I can't do that with my scope because my scope is grounded. It's grounded through the Ethernet. It's grounded through all the other connections. I can't hook the negative to a power supply like that, but there's positive and negative to channel 1 right across the resistor. So I love it for the floating ability. So yeah, can't say enough about.
Cool. Yeah, I try to usually make the device itself, the device under test, floating, and then I'm less likely to. I mean, you still have to be really careful, but I'm less likely to accidentally short something through an instrument ground or whatever.
Right. Well, you know, you'd be proud of me. Remember when we started talking a couple of years ago, I talked about how I used to do this, right?
Yes.
Everyone who's worked in live,
away.
Production has done that.
But I'm throwing them away now. When I find one, I throw it away. So I'm now convinced you can't float the ground on any modern scope, but I'll still tell you can on the old ones. So cool. Hey, Mike, you built a PC board this week, right?
I did. Yeah. This is my first MOSFET based thing. I've never done so this is basically a board, an adapter board to drive a solenoid lock. Where'd it go? Oh, here it is. One of these kind of things, you know. This is basically, it draws 800 milliamps while the thing's turned on. So you have to and I wanted to switch it from this is basically an adapter that takes I2C and it's got a little GPIO expander on it to turn it into, you know, a little control that you can do. And for me, the new bit was like properly driving this. I can't do this when I'm looking in the screen, but this thing here, basically I had previously I had like a BJT or Darlington based power transistor, and that thing would get hot when you're driving this thing.
Right.
So actually I'm working with Frank Buss and he's like, hey, you should probably do one of these, a MOSFET. So I went and did it. So this is my first MOSFET and it works. This thing stays cool.
They're way more efficient. So it was pretty typical to drive a solenoid or a relay coil through a Darlington BJT. That's kind of like the industry standard well into the 90s.
Yeah. Okay.
But you always have dissipation. You always get dissipation from the base current, and it's not necessarily the base current driving into the base. It's the base current of the second transistor.
Right.
It's
okay.
It's always got that 0.7 or sometimes if the whole thing's driving a lot of current, you're probably going to have it's never going it'll be in saturation, but it's never going to get lower than about a volt drop across it. So if you're pushing an amp through it, and a volt, you've got it's dissipating a watt. So if it's on a printed circuit board, 1 watt. If it doesn't have heat sinking or anything, it's going to get hot.
Yeah.
So
this thing stays cool.
MOSFET, it's equivalent to a 0.03 ohm resistor.
Yeah.
It's just way better. It's like another piece of circuit board trace, really.
And it's also, I noticed, like, it does let the current flow through this. If you have kind of like this thing is designed to work at 12 volts, but if you have something that's slightly lower or whatever, this MOSFET's better at that because it's got such low resistance. It'll just let the stuff flow right on through.
What is it you're actuating there? Like that's a solenoid. Is it for turning on a valve or something?
Oh no, it's actually for demo purposes for a product we're working on at work. But this is just because it gives a nice satisfying view of a click to show you it working. Yeah. So yeah.
So now you used an IR 540. What'd you use?
Yes. This is IR
544.
Not IRL. IRF. 540. IRF 540. Yes.
Right. That's a very standard.
Yeah.
It's a very standard MOSFET for this kind of application. They're called IRF because the company that designed those was originally International Rectifier. They were based in Temecula here.
Yeah.
Just up the road from Escondido, where I live.
Yeah.
Right.
And they were acquired.
XFETs.
They were acquired a couple of years ago by Infineon.
Ah, okay.
So now they're part of Infineon, but they were International Rectifier. They took over the market for MOSFETs because they came up with this, what you were holding up there, Bill, the HEXFET. They came up with a silicone structure that was basically equivalent to thousands of MOSFETs in parallel. So they had really low RDS on, but they could still switch on and off relatively quickly.
Yeah.
And so they invented the HEXFET. It's called a HEXFET because it was a honeycomb pattern in the silicon.
They look like little pockets. Yeah.
Yeah.
And speaking of that,
they should have illustrations of what that looks like in there.
Those are evidently in this load. Those are evidently on the heatsink in here. And VoltLog looked at his and he's like, those look like they're clones. They're not really.
Wow.
Yeah.
Yeah, that's it. So now
didn't know because they had old date codes on them. Like
that's right. So unless you're buying Infineon, they probably aren't HEXFETs. But there are tons of other manufacturers now that make them with the same part numbers because they design them to be equivalent, like close enough matching in characteristics. But yeah, there's a lot out there, but they may be VMOS or trench MOS or DMOS transistors. They aren't necessarily HEXFETs because they would have to license that technology.
Yeah.
BFETs were vertical FETs, right? They tried that before they ended up in HEXFETs on their way to.
And that's still Vishay and ST, I think, still make a lot of their MOSFETs in the V process.
Yeah.
I'll see if I can find a picture of what that really means.
And we mentioned IRF versus IRL.
Right. So what's the L, Mike?
Logic level. And
right.
I went with the IRF because that's what I had on hand. I didn't want to. I was putting together a prototype that I needed quickly, so I didn't want to mess with I didn't want to do the thing where I would buy a part that I didn't have on hand to breadboard. Basically, I don't have enough confidence in myself to get it right without trying it first.
And I built a little control board and threw a little FET on it, just like you did. That's just a little switching dynamic board.
So logic level means like the is it called the gate?
Gate threshold.
The gate, you could drive it using like 3.3 volts and it would work. Whereas an IRF, you got to get way up high.
If you really want it to go to low RDS on, you want to push it with 10 or 12 volts.
Yeah.
So, Mike, have you heard of DVDT with FETs? DV over DT.
Like, are you talking about calculus now?
No, change of voltage over change of time.
Yeah.
The delta B, delta T.
Okay.
So what? Yeah. Have you run into why they list that on MOSFETs?
No. So this sounds like something that would apply to a capacitor, maybe. Okay. So how does it have to do with a MOSFET?
Well, you can accidentally turn on your MOSFET by giving it too fast a voltage.
Okay.
Right?
Like it might.
Am I saying that right?
Yeah.
Like you might rise up a little bit and it might trick it into.
Yeah. It goes avalanching right through is the way I envisioned it.
Is that because there's a little capacitor on the gate and you fill up that capacitor, or?
You know,
Oh, wait.
I don't know the physics reason for
mechanism,
that,
yeah.
but that capacitor on the gate is actually, there's a formula for that. It's the capacitance on the output looks like 1/10 of the capacitance on the gate. And so if you're driving 1,000, picofarad, it looks like 100 picofarad. To the one in front of it, it looks like 10 picofarad. So that's the math that the NMOS guys used to do back in the days at Commodore.
So if you have like a signal that rises, but you didn't intend it to go up high enough to turn it on, just the speed of it might have accidentally turned the thing on.
Yeah. That's what I recommend it's the memory is so old in my brain that I can't do it justice, but that's
well, that's part of what I call experience. You know the problem exists, you go look it up, and you read up on it again, you're like, oh yeah. Whereas like if you don't have that experience, like someone like me, I would be like, why is this thing failing? Why is it broken?
I turn it on fast.
And then I'd be like, Bill, what's it doing? He's like, oh, there's this thing called DVDT.
Yeah. Yep. So, well, cool. So I'm kind of.
I just wanted to throw this.
Yeah. What you got?
This is.
There it is. There's a picture of hex FET.
Oh, hex FETs look like hex. Yeah.
That's why they're called hex FETs. It's like a honeycomb sort of structure. So they came up with this very creative way of masking them.
But surface area.
This is not a particularly high resolution image. This is probably a scan of what was in that data book that Bill was holding up to the camera before. But basically, the gate is a very thin metallization in a honeycomb pattern, and the source is actually then you have your oxide insulation layer, and then the source is plated over that. And so you end up with this really low on resistance, but still not too bad as a sacrifice for gate capacitance. You can still keep the gate capacitance low enough. And so that company took off because every switching power supply went from BJTs to hex FETs pretty much overnight. Any name brand switch mode power supply, old flyback and push pull switch mode power supplies in desktop computers from the late 80s were using BJTs, and they were about 70 to 75% efficient at full load.
So that's cool. This innovation happened in the 90s, huh?
Not great. Yeah. Then in the early 90s, they invented this and started publishing all these app notes how to redesign switching power supplies using hex FETs and getting well over 90% efficient. And now today, like it's considered a bad design if you design a switching power supply and can't approach 96 or 97% efficient at full load. I say at full load because that's the only time you can be most efficient.
Right. It goes down as the load goes.
Because you have all that supporting circuitry around it, and lots of other reasons. But as the load drops, your efficiency drops.
Cool.
So and then just to compare that, the VMOS that was the technology that came before.
Oh, good.
Yeah. Let me zoom in on that.
Oh, good picture. Yeah.
It was this kind of deal, and. So this is what you'd get with some MOSFETs made by, say, ST Microelectronics or, other manufacturers. On Semiconductor, which used to be Motorola, they tend to use this kind of approach. And Vishay. And today you can get VMOS transistors that, according to their data sheets, they're just as good as hex FETs. So I guess they've done further optimizations on this process.
Right.
But they're also not bad because you can still design these to have a reasonably low gate capacitance. It's just different methods of solving the same problem, which is how do we keep gate capacitance low and reduce the on resistance when this thing's turned on? So, anyway.
Cool. Yeah, very cool.
I thought everything was invented in the 70s. I didn't know you could still make innovations happen these days. That's cool that they're fundamentally pushing that forward.
Yeah. Very cool.
Yeah. Well, the next thing after this is gallium nitride, right? It's using different materials. So I've I've been involved in a project for another company. I won't say any names or anything, but we were using a gallium nitride FET, and those things are really impressive.
Yeah, we should talk about Dan. Yeah.
Where it's like smaller than a grain of sand on the board, and the thing can do incredible things.
Right.
They're designed, they're targeting things like they're high electron mobility transistors, so they're good well into the RF, and they're targeting things like very fast switching of lasers for LiDAR. So pulsing a laser really with a really sharp pulse rise time. And yeah, so you can the DVDT on those is incredible. That's their superpower. Really fast slew rate.
Right. Yeah, in the pulsar that I have, the nanosecond pulse generator uses a laser driver from Leo Bodner.
Yeah,
we talked about those like over a year ago.
Yep.
And,
so there's a gate driver that'll do sub-nanosecond pulse to the gate, and it's like they're expensive. Yeah. They're like $30 for a tiny little chip that's chip scale package. You can hardly see it. The gate driver is bigger than the FET itself because of the packaging and because it has to have extra pins. It's a 6-pin device.
Right.
And they're like $30 each in one-off quantities. So they're not cheap. Well, maybe they were $10 each, but they were expensive. And then the FET itself is a 4-pin package that's so tiny. It's like smaller than a grain of sand, but it'll do sub-nanosecond rise times.
I fell into that same trap. I was like, how fast can I make the rise time be on something? And I was digging into it. And then I was talking to Bill. It's like, yeah, he was in the same thing. I mean, ultimately, you're just like, I'll just buy the thing from Leo Bodner.
Yeah. We were both trying to make really fast pulsars. I'm like, oh, I ended up paying $70 and getting the best one, far better.
Well, but here's the thing. Mark Harris, who does really cool videos and projects, people might have seen him. He doesn't work for Altium, but he does stuff for them as a contractor. Mm-hmm. He showed me. He just did a dead bug pulsar using transistors avalanche mode.
Okay.
I think it was avalanche.
Right.
And got down to very close to 1 nanosecond, even just doing dead bug with half the components were through hole even. So if
impressive,
if you know what you're doing and you have a good ground plane, like that's pretty amazing what you can achieve.
So I had, when I researched doing a fast pulse generator, I actually went through the Hackaday articles, and there was one that wasn't too shabby, and it was a wetted mercury switch. And they were getting like 40 nanosecond pulses out of it or something like that.
Yep.
So yeah, there was a lot of ways. Avalanching was another way, but then, like I said, I found Leo's circuit and like, oh, let's go with this.
So Leo's using a high-speed gate driver. Is that what it is?
It's a laser driver for it's a laser driver.
Yeah.
So and Mike, you have a CSA 803, isn't that kind of how this started?
Yeah, I have the same thing.
Communication signal analyzer.
Yeah,
right. We threw it on our CSAs, and we're like, "Oh, look, seconds."
It's insane. Yeah.
Yeah. Oh yeah, I could see the vias on the board. That was cool. I'll have to fire up the CSA again if it still works. That's the thing about old equipment. The capacitors are still getting old, even if it worked the last time I turned it on.
Every time you turn it on, you take a chance.
I struggle. Like even finding a bargain on eBay with some old oscilloscope or signal analyzer that has the bandwidth, but they still, whoever's selling it, the listing just says it powers on. We haven't done any other tests,
right?
And they still want over $1,000. It's like, come on, guys. I mean, if you want to charge real money for a used bit of gear, at least give people the assurance that they're not going to have to do repairs on it.
Every piece of gear I bought off eBay that says it's working, you'll find something somewhere in the machine that's broken. That doesn't quite live up to spec, and you have to go in there and dig into it and fix. And for me, it's fun because it's a learning opportunity. But if you're, from a financial standpoint, it's like, come on,
I don't want to do that. I don't have the time.
If you just want to buy a thing that works, then that's not the way to get it. Yeah.
Right.
Yeah, and then it's like, we'll buy something new. Well, then I'm going to pay, money. So then it's going to be 10x the cost. So
what I do sometimes is I look on eBay, find equipment that's for sale by a reseller, a true used equipment reseller. Now I'll contact them out of band and try and get a warranted, instrument out of them. So that's been my way around it. So, well, great. So it's 5 after. Anything else to talk about while we got the three of you here? The three of us? No? All right.
No, well, I mean, that time actually went by pretty quick.
It did. It did. So
It's always fun, yeah.
Well, I want to thank you, Mike, for being able to jump in like that. Yeah. And Ben, good to see you as always. And this was fun. Now I have to go make the thing work that I bought my dynamic load for, but that should be fun also. So
yeah, give us an update next week.
If you drop kick that Rigel out your window.
Drop kick the Rigel. DTR, drop kick.
That's what I want to say. Like, how long is Bill's patience before he's like,
Yeah, he could tell I was losing my patience over the Discord.
It's not a piece of HP gear. Yeah, you want too much out of it.
Oh, very cool. All right. Well, we'll see everybody here next week, and you all have a safe weekend. And that's to everybody out there.
Yep. Thank you.